Right, yes, so hello everyone. My name is Stef Verpoest. I'm from Ghent University in Belgium, and I will present to you some work we did on high energy muons in air showers detected with IceTop and IceCube. And so this is of course in the context of the muon puzzle and hadronic interactions, which was nicely introduced on Tuesday morning by Lorenzo. So let's start with the detector. The IceCube Neutrino Observatory is a multi-purpose particle detector at the geographical South Pole. The main detector, IceCube, sits 1.5 kilometer below ice and consists of a cubic kilometer of instrumented volume with about 5,000 digital optical modules. On top of that, at the surface, we have the IceTop array, which consists out of 162 ice Cherenkov tanks on a triangular grid on a square kilometer of surface. And it sits at a high elevation of about 2,800 meters, corresponding to about 700 grams per square centimeters in depth. And the size and the density of the array may make it ideal for the detection of cosmic rays in the PeV to EeV energy range. And so combining these two detectors, we actually get a very unique air shower detector because we can, at the surface with IceTop, measure the abundant electromagnetic component close to the shower maximum, as well as muons, typically in the GeV energy range. And if the geometry allows it, we can also detect a high energy muon bundle, which reaches the in-ice detector that is starting from a couple of hundred GeV. And we refer to this component as the TeV muon component. And yeah, this setup allows us to perform unique tests of hadronic interaction models because we can measure these different components. And this is, for example, illustrated in the plot here, which shows the ratio of muon energy spectra in air showers predicted by post-LHC interaction models compared to Sybil 2.1. And so, for example, what we see is that in the low energy muons, there is an increase in all models. And this is where IceTop and most air shower arrays measure. But with the in-ice detector, we can also measure in this energy range here. So as I said, around the TeV, and there the predictions by the models are not so uniform. So when such a coincident event happens in IceCube and IceTop, the signals typically look somewhat like this. So to the signals in IceTop, we will perform a standard air shower reconstruction fitting the lateral distribution function and the shower front to obtain the shower direction and the core position. And from the lateral distribution, we also get the shower size S125, which is a good proxy for the primary energy. To the in-ice signal of the muon bundle, we perform an energy loss reconstruction along the track that was reconstructed with the IceTop reconstruction. And we do an energy loss reconstruction in segments of 20 meters perpendicular to this track. And so that leaves us with a vector of deposited energies by the muon bundle throughout the detector. So as shown here with this example vector. And in this analysis, what we do with these reconstructions is we feed them to a neural network. I feed the shower size, the reconstructed zenith, and the energy loss of the muon bundle to a neural network, which through a combination of recurrent and dense layers reconstructs two quantities, the primary energy of the shower and the number of muons above 500 GeV in the shower, as defined at the surface. And so this neural net is trained on Monte Carlo based on Sybil 2.1 with 4 components: proton, helium, oxygen, and iron. And we look specifically here, of course, at these coincident events. We also ask that the shower core is contained in IceTop, and we look at very vertical showers with zenith angles below 18 degrees. And so the figures here show the correlation between the reconstructed and the true quantities as obtained from the neural network. And so we see that respectively in the top and bottom plot, both the primary energy and the high energy muon multiplicity get reconstructed with a pretty good resolution. And especially when you go above the IceTop threshold of about 6.4 in log E. So with this neural network and this reconstruction of these two quantities, what we want to do is to obtain the average muon multiplicity in bins of primary energy. And so again, this is muons above 500 GeV in the shower. And so what I show here in the top plot is actually the predictions of this muon multiplicity as function of energy in Monte Carlo, shown by the lines, compared to the reconstructions we get from the neural network. And these are shown by the crosses. And so we see that in general, this relation is captured quite well already by the neural network for all elements. However, there are some systematic biases in this reconstruction. And that is shown here in the bottom plot, which shows the ratio of the crosses and the lines in the top plot. And so we see, for example, that for proton and iron, we get a over and underestimation typically of around 10% in the amount of muons. So yeah, we want to deal with this, of course, in data, and to do this, we fit these ratios with quadratic functions, and we will use later on the proton and the iron fits as correction factors to correct for these reconstruction biases. Of course, as you see, the exact correction that needs to be applied will depend on the mass composition. So to deal with this, we make use of the fact that the measurement we are performing of the number of muons has itself composition information, and we use this to define an iterative procedure for this correction. And this is illustrated with just an example here on Monte Carlo in the plot on the right. So what is shown here in orange is actually true values of muon multiplicity in Monte Carlo for an H4A flux weighting, just as an example. And they are scaled to, for better visibility to the expectations of proton and iron Monte Carlo in such a way that pure proton would be at 0 and pure iron here is at 1, as shown by the blue line. And so what we do is when we, on this Monte Carlo example, apply the neural network, we get a kind of a first guess, which is shown by the light blue dots. And so that is already, I mean, kind of in the ballpark of the true values. However, we use this first estimate to define an effective correction factor, which is defined here by a linear combination of the proton and iron correction factors. And the way in which they are combined is defined by the composition estimate we obtain from the muon multiplicity measurement. So we performing or applying a neural network, we get a first estimate of the muon multiplicity. We use this to define a correction factor, which gives us a new update of the muon multiplicity and so on, and we repeat this until convergence. And then we see we converge here to the dark blue dots, which line up nicely with the Monte Carlo truth. So to kind of prove that this procedure of neural network and correction works well, we performed a bunch of tests on Monte Carlo. So here the plots show the performance on pure proton, helium, oxygen, and iron. And what we see is that we get good agreement for the reconstructed muon multiplicities for all of these cases. And we have tested that this works in general well also for mixed compositions. So knowing this gives us confidence to apply this to experimental data. And this is what I show on the next slide. Now, unfortunately, due to time constrictions, the plots here are made with only 10% of 1 year of data. However, that already gives us pretty good statistics in a large energy range, which is one of the benefits of working below the ankle. And so the obtained result is shown here compared to predictions of Sybil 2.1. So we see that the multiplicity goes from a couple of tens muons at 2.5 PeV up to over 1,000 muons at 250 PeV. And the results are bracketed nicely here by the proton and iron expectations. The measurement, of course, comes with systematic uncertainties, and the main ones are these the following detector uncertainties. So this is due to the snow accumulation on IceTop, which influences our reconstruction. Then there's the uncertainty in our charge unit, so the vertical equivalent muon. And then there is a large uncertainty due to the properties of the South Pole ice, so of the ice detector. And this is the largest one. And so the shifts due to these systematics on the result is shown in this plot. And so we will add all of these in quadrature to obtain the total systematic uncertainty. Now first, before going to the final result, the measurement we do is of course model dependent. we have so far worked with Sybil 2.1, but we can also obtain these correction factors from different Monte Carlos. So for example, we have here available also QGSJet 2.04 and EPOS LHC. These data sets are a bit smaller. They are limited to 100 PeV. However, this is of course also interesting to obtain the results under the assumption of different models. So with these correction factors that we get from Monte Carlo, we can interpret the experimental data under these different model assumptions. So the results for the average muon multiplicity above 500 GeV in air showers are shown here for the 3 different models we use. Unfortunately, we don't have Sybil 2.3 CRD yet, but this is under production, so that's hopefully coming soon. But yeah, so what we see here is the multiplicity results with the shaded area giving the total systematic uncertainty. And of course, they are always compared to their corresponding Monte Carlo predictions. And so what we see is that they're always nicely bracketed by proton and iron, which is good news. On this slide, I compare in a bit more detail how the predictions of the different models compare to each other. For example, in the left plot, you see the predictions for the multiplicity for Sybil 2.1, QGSJet, and EPOS, compared also to kind of an average result I obtained from the 3 individual results with an envelope describing the spread of the models. And so, what we see in the predictions, first of all, here is that QGSJet predicts most of these high energy muons, while EPOS predicts the least. And then if we compare the individual model results to the average here, just to see kind of how model dependent, let's say, the result is, we see that they only vary by about 3%, which is a lot less than the difference in the muon predictions. So a more clear way to interpret these results is by plotting them in the so-called Z scale, where the result obtained in data is compared to predictions for proton and iron in Monte Carlo. So the results are shown by the black dots, and the brackets now give the total systematic uncertainty. And we compare them also here, the results, to the expectations from different modern composition models. So these are H3A, the 3-component GST, and the GSF model. And so what we see is that the results we obtained from Sybil 2.1 and QGSJet, their composition interpretation is very similar and agrees well with with the expectations from these composition models. And EPOS is consistent with a slightly heavier composition, mainly because it predicts less muons than the other models. Thank you. So to summarize, I performed a first measurement of the TeV muon content in air showers with IceTop and IceCube. And we obtained results for Sybil 2.1, QGSJet, and EPOS LHC between 2.5 PeV and 250 or 100 PeV, depending on the model. So the results are shown here again compared to different expectations. All the results are bracketed nicely by proton and iron, and have in general a pretty good agreement with composition models, although EPOS LHC yields a slightly heavier mass composition than the others. Then for an outlook, of course, we want to add more data to this study. This is also coming soon, and there are also several other improvements we can do, such as increase the phase space, reduce the systematics. But what I really want to highlight here again is the interesting opportunity we have with IceTop and IceCube to measure both measure muons in both the GeV and the TeV energy range in our coincident events to perform unique tests of hadronic interaction models. And what I show here on the right, these plots are actually results of a measurement of the density of GeV muons in IceTop at large lateral distance. And what we see here is that there is, first of all, at the energy range, IceTop looks at no evidence for a muon deficit or muon excess. But we do see tension in the results of these GeV muons compared to the TeV muons. So I will flip back and forth once here. So these are the TeV muon results. They all show a nicely mixed composition in agreement with expectations mostly from different composition models. Going back to the GeV muons, we see that the post-LHC models actually are consistent with a much lighter composition compared to the TeV muons, which may indicate that these models actually predict too many muons in our energy range. But this is, of course, something we want to study more in detail in the future. We also like to look at things like GeV-TeV muon correlations on an event-by-event basis, and so on. And then lastly, with the upcoming upgrades of IceCube Gen 2 and the surface enhancement, we will also be able to improve our measurements and our tests of hadronic interaction models with, for example, improved systematics and an improved measurement of the electromagnetic component with, for example, the radio antennas, where we get an X-max estimate. So that's it. Thank you.
Thank you.